9 asks us to rank atoms or ions by their size or their ionization energy. So first, let's just remember our general trends. And the nice thing that I mentioned in class is that all of our trends are either kind of up and to the right or down and to the left. Atomic radii, size, is one of the ones that will increase as I go down and to the left. So, generally speaking, the further down I am, or the further to the left I am on the periodic table, the larger the atomic radii will be. It turns out that that trend is the opposite for ionization energy. Our ionization energies down in the bottom left with things like francium tend to be among the smallest, and ionization energies up by fluorine or helium tend to be the largest. So our ionization energy increases as we go up and to the right, and our atomic radii increase as we go down and to the left. And both of those are due to the combination of the fact that as I go down a group, my N increases. My electrons are further away from the nucleus and easier to remove, and the atoms themselves are larger due to that further distance. As I go from left to right across a period, remember what happens there is that Z effective increases. That effective nuclear charge, the pull that the outermost electrons feel, gets stronger and stronger as I go from left to right across a period, and that has the effects of, one, making those electrons harder to remove, raising the ionization energy, and it also has the effect of holding those electrons tighter and closer, reducing our atomic radii. With that general principle out of the way, we can now dive into the specific elements that you're asked to compare. So first, we have fluorine, chromium, aluminum, and potassium. So first things first, it's good to go and find those elements in the periodic table. We have fluorine here, chromium there, aluminum there, and potassium there. So the first thing I can see is potassium is the potassium and chromium are both here in my fourth row, my fourth period. Then my aluminum is here in the second period, and fluorine is here in the first. Knowing that this is in the first period, that is going to tell me right away fluorine is going to be my smallest element. Its electrons are in its 2p compared to 3p, 3p or 3d or more, or others for the other elements. So fluorine is my smallest. Now, which of these is the biggest? I'm thinking about potassium, aluminum, and chromium. Already I can see, well, aluminum has a valence electron that's in the 3p compared to the 3d or the 4s. So that one is out. And this is the 3d compared to the 4s. So we've got like sort of that choice there. But then remember that Z effective increases as I go from left to right. So that effective nuclear charge that chromium feels is bigger than the effective nuclear charge that potassium feels. That means that chromium are held closer, and potassium would be my largest. So I would circle that one to be the largest. And then my predictions after that would be large. If I'm doing sort of from 1 to 4, smallest to largest, I would rank them in that way. Now, size here for our next question asks about sulfur 2-, magnesium 2+, aluminum 3 plus and chlorine minus. So already we've got a bit of a tougher question here. All of these are either 3s, are in the third period. So we can't just immediately go to there. And worse, these are charged. So we should really think not just about the size of these as atoms or elements, but the size as ions. One thing that we can notice is that for the magnesium and the aluminum, these are positively charged cations, which means that we're going to remove electrons away. Magnesium 2 plus is going to actually, if I see when I remove 2 electrons from magnesium 2 plus, it has the electron configuration of neon. Right? I'll just write that out to demonstrate. 1s2, 2s2, 2p6, 3s2 is my magnesium. Then magnesium 2 plus, I'll need to take away the 2 outer electrons, leaving me with 1s2, 2s2, 2p6, the same as neon. And you can also hopefully see that the aluminum 3 plus is also going to have the electron configuration of neon. So I would say that these two species are isoelectronic. They're both going to have only 10 electrons. So when we have the same number of electrons, the next thing that we have to go off of is our Z effective. And here I can see that aluminum versus magnesium, aluminum has 1 extra proton due to it being atomic number 13 compared to 12, which means that the Z effective will be bigger in aluminum than magnesium, and that will hold those electrons tighter than magnesium. So I expect that my aluminum radii will be smaller than magnesium 2 plus. And in fact, those electrons are 2p electrons. They're in n equals 2 compared to our sulfur and chlorine electrons. So we can say that of magnesium and 2 plus and aluminum 3 plus, those are going to be our smallest. And aluminum being even smaller tells me aluminum 3 plus is the smallest element. Now, if I think about sulfur 2 minus and chlorine 1 minus, or as they're referred to, sulfide and chloride, those two things are also isoelectronic. They have the electron configuration of argon, right? We can see that sulfur 2 minus, sulfur is 1s2, 2s2, 2p6, 3s2, 2p4, and then sulfur 2 minus will need 2 extra electrons. So we go from 2p4 to 2p6. So now, again, I have to make my judgment call based on my Z effective. Sulfide and chloride are isoelectronic with one another, but chlorine with that 17 proton nucleus is going to have a bigger Z effective than sulfur with its 16 proton nucleus, and therefore my sulfide will be my sulfide will be larger than my chloride, and so sulfur 2 minus is my largest of my elements. That does our atomic radii trends. Now let's talk a little bit about ionization energy. Again, we've got our trick here. Ionization energy increases as I go up and to the right. And so I can see right away that between fluorine, chromium, aluminum, and potassium, that fluorine is the one that's furthest up and to the right, and potassium is the one that's furthest down and to the left. And so that tells me that fluorine is going to have the biggest ionization energy, and potassium is going to have the smallest ionization energy. So we very quickly size this up just from that up and to the right trend. Ionization energy for silicon versus sodium versus oxygen versus carbon. Give me a moment. Again, I can use my up and to the right, down and to the left trends here to tell me that my oxygen is the one that is furthest up and to the right, and my sodium is the one that is furthest down and to the left. And so sodium will have the lowest ionization energy, and oxygen will have the highest ionization energy. Silicon versus carbon, if I wanted to rank all of these, I would go after sodium. The next lowest would be silicon, then carbon, and then finally oxygen. Now down here in the additional practice question, we have a period 3 element. So we're thinking about something in this row here. And we notice that its ionization energy goes up, maybe like it triples here. It goes up here again, and then between 3 and 4, it goes way up, right? 500 to, or 600 to 1,800, 1,800 to 2,700, then 2,700 to 11,000. That's a big jump here. And so that tells me that between the third ionization energy and the fourth ionization energy, I'm going from n equals 3 down to n equals 2. And so now the question is, what element can lose in the third period, could lose n equals 3 electrons, and then the next one would be n equals 2? Well, I could do this a couple of different ways. I could go to the periodic table, but I actually like thinking about this from my electron configuration. Here is a full, here's a sort of a full n equals, this is my configuration for argon. If I lose 3 electrons from argon, I get to this point. So that's no good. But if I started, let's say, here, then my first ionization energy would be to this. And would be, a good size. My second ionization energy would be going to this. My third ionization energy would be going to that. And then my fourth ionization energy would be pulling an electron away from the 2 level. So that must be the one that I'm thinking of. So let's undo and work our way back. That tells me that whatever species, this is where we were, whatever species we're looking at is going to have 3s2, 3p1 configuration, and that is my aluminum. You could count up these electrons if we wanted to confirm that. 2, 4, 10, 12, 13. I'm looking for something with Z equals 13, and that is aluminum. So that would be my answer. Hopefully this helps.